Hello everyone. So this is our lecture on 3D kinematics and kinetics of rigid bodies, or you might call it dynamics of rigid bodies. And again, this is one of those topics that if the time allows, we are going to cover that. But anyways, I made the video, so if we have the time to cover it and make it a part of the course syllabus and assessment, will do it. Otherwise, this can be served as serving as a reference for you if you are interested in knowing about how to find the equations of motion and the kinematics equations of rigid bodies in 3D. And this is chapter 20 of your textbook. So far all we have seen is 2D. Right? But for many engineering applications, we cannot just get away with 2D representation of the problem, right? So most of the problems, as I said, we have seen so far, we could get away with 2D because the object was thin, because the motion was only in 2D, or many other cases. But for example, when an airplane flies, you know, an airplane has 3 different rotations, not just a single rotation in plane, perpendicular to a plane or along a specific axis, like what we had been seeing so far along the z-axis, right? If you move on the xy plane, you only have one angle of rotation about the z-axis, but you know, airplane has 3 angles, right? So if you basically rotate about the longitudinal axis of the airplane, we call it roll. If you turn about the axis that is perpendicular to the plane, plane formed by the wings and the fuselage, you call it yaw. And if you rotate about an axis that is the axis of the wings, we call it pitch. Right? So it has 3 angles, and we have to consider the motion of an airplane to be 3D. Or if you have gyroscopes, if you have vehicles that are moving on short distances and on areas where the ground is not perfectly flat, right? And many other things, especially even vehicles when they go around the traffic circle, that could be another case. Non-planar robots, and so on and so forth. So in these cases, we typically resort to a secondary reference frame. Why? Because it is easier, more convenient to measure, sense, describe the motion of the object with respect to the secondary frame than with respect to the primary frame that is inertial and most of the time is stationary. Like, you might say, like what? And the example I mentioned here are robot encoders. So when you have a serial manipulator, right, and each encoder and each one of the joints of the robot is measuring the angle of rotation. The angle it is measuring is with respect to the previous link, right? So let me tell you what exactly I mean. So for example, if I have a 2D planar arm and it looks something like this. So this is a 2D robot. I'm not even going to go in 3D. So they're pivoted here, and then this link number 1 is pivoted to the ground like that. And let's say at the end of this, you have an end effector, something like this. That is rigidly connected here. Okay, so now, if you consider an inertial frame here that is not moving, not rotating, and call that frame YX, so this is the inertial frame, primary frame, if you have an encoder here at this joint, which measures the rotation of this link 1. Well, what angle does it measure? It measures it with respect to this inertial frame because it describes the motion between link 1 and the inertial frame. So it gives you this angle theta 1, right? But now, if you have another encoder here at joint 2, which gives you the rotation, what angle do you think it would give you? Well, it is measuring the motion between link 2 and link 1. So for it, link 1 acts like a fixed link, link 2 acts like a moving one. So what it really measures is not this angle theta 2. It is not measuring this theta 2. Because it's measuring it with respect to link 1, not the x-axis of the inertial system. So what it really measures is this angle. If you continue link 1, it is measuring this angle, the relative angle. Okay? So here, if you add a secondary frame at this joint like this, and call it small x, small y, it is convenient, not convenient, it's only possible to describe the rotation of link 2 with respect to this moving frame or rotating frame xy that is rigidly attached to link 1. So this frame xy is not stationary. It is rigidly attached to link 1 and it is rotating with link 1. So when you are on this secondary frame small x, small y, you can never sense angle theta 1. What you can only sense is angle theta 2. So you can only measure relative to the secondary frame, not to the inertial frame. So not only we have to use the primary frame, we have to use a secondary frame. Or another example is a mobile robot. So if you have a mobile robot, and this robot is trying to use its LiDAR or Kinect or any sensor that measures depth and tries to create a map of the environment. So let's say here you have some obstacle, and you have another one here, and so on and so forth. And you send your robot, your differential drive robot, you send it in. Okay, so this is one tire, this is another tire. And this robot has here a sensor. And this sensor is going to measure distance and then creates a map. So how does it do it? Well, this robot sends its signal, acoustic, infrared, whatever it is, to the different points on the object. It bounces back, it basically receives the reflected signal, and then based on the time of travel measures the distance from here to here. And then at this point the robot knows that it has rotated so much with respect to x-axis. So basically if you call this axis x of the robot and you call this axis y of the robot, so this angle, if you draw the a line parallel to the stationary x, this angle is the angle of the robot that it has rotated, theta. So it knows how much it has rotated. It knows its position of this centroid here with respect to the origin. And once it knows this distance d, it can exactly locate this point, right? But if, again, as I said, this d that you are measuring is measured with respect to which coordinate frame? with respect to the coordinate frame that is attached to the robot, right? It does not measure the distance from this point D directly to the origin of the fixed frame. So you see here, I need a secondary frame with respect to which my sensor is measuring some stuff, and then I would add the current position of the robot to the position of the point with respect to robot to find the position of point with respect to a fixed world coordinate, okay? And then I can add more points and then create a map of the environment. So whenever it comes to sensors, most of the time especially, it is convenient that you have a secondary, sometimes a tertiary reference frame. Now, in this case, this is what we do. As I said, in these examples I mentioned, the secondary frame is typically rigidly attached to the rigid body that we are going to study. Now, in this case, it's not mandatory. So in this case, the secondary frame is not what we call body attached frame. It can have an arbitrary motion with respect to the inertial frame and not be attached to the rigid body. So in this case, as I said, the secondary frame has an angular velocity of cap omega with respect to this primary frame. Okay? And then the angular velocity of the rigid body, small omega, with respect to the inertial frame, but written in terms of the axis of the secondary frame. Why should you write it that way? Because this is served as the reference for measurement. And then you might say, well, can't I say this omega is also with respect to the secondary frame? You can, but in this case, in this derivation, here, this omega is not rigid body with respect to secondary, it's directly rigid body with respect to the primary, which is basically what we need to find at the end of the day. So if we call that omega, but these ijk again are the unit vectors along the secondary frame, not primary. So if I write my omega in terms of these axes, so omega xi, omega yj, omega zk, now if I want to find the angular acceleration of the rigid body with respect to the inertial frame, I have to take time derivatives. And omega x, omega y, omega z could be variable, so they can have derivatives. But not only that, these vectors I, j, k, as I told you in the past, they also have derivatives. Why? You know, they are unit vectors. Their magnitude is always 1. How come they have derivative? They have time derivative. You're right, because they are attached to a frame that is rotating, and it's rotating with angular velocity omega. So their time derivatives, di over dt, dj over dt, dk over dt, are omega cross I cross j cross k. So these unit vector derivative terms, if you combine them together, you can write them as omega cross omega. And this is the term due to change in magnitude of these, okay? So this comes to what we have seen in the past, and the theorem that I mentioned, and I mentioned it one more time for your reference here. If you remember, I mentioned this important theorem that if vector A has a constant magnitude and this vector is attached to a frame that is rotating with angular velocity omega with respect to frame XYZ, then time derivative of that vector A as calculated in this frame XYZ, it is going to be omega cross A. Okay, this is the theorem that I mentioned over and over, and we're going to use this guy a lot. That's the basic of the kinematics of rigid bodies. We use this guy a lot. And this is what this frame is. And I'll show you a graphics of that as well. So here I have this frame XYZ. This is the inertial frame. And here in this frame small x, small y, small z, which is a frame that is rotating, I have some vector A from this point to this point, which has a constant magnitude, 2 units, 3 units, so on. And this moving frame is rotating with respect to this primary inertial frame with angular velocity omega. Then if I say what's the time derivative of vector A if I describe it in the small frame, in frame small xyz, how much is that? Well, you say it's 0. Why? Because this is a vector with a constant magnitude, and it is basically a fixed vector here, not only magnitude constant, it is a fixed vector. And it does not change in this. If I put a sensor here to look at the variation of this vector A, it cannot sense anything. Why? Because that sensor also rotates with this vector A, with omega, so it's not going to sense anything. But if I put my sensor here attached to this fixed frame and now say, hey, does this vector A changes with respect to time? Yes, there is. Although its magnitude is constant, but it does change direction, and the change due to direction is omega cross A. Okay, so that's exactly what we are using here. We are saying that, well, true that this vector omega, which is angular velocity of the rigid body with respect to the inertial, is written as omega xi, omega yj, omega zk, true, but it is written with respect to the secondary frame, the unit vectors of which are rotating with angular velocity cap omega with respect to the primary frame. So when I take time derivative of omega to find alpha, alpha is going to be time derivative of these components times ijk plus what? Plus omega x times time derivative of ij and k, and those time derivatives of ijk are going to be cap omega cross ijk. So you're going to get this formula, where again here this omega dot term is the change in magnitude of these omegas. This is due to rotation of the reference frame, which is the secondary frame here. Okay, so this is this formula written in a vector format for you. Now, because what you have seen in the past is only alpha equals omega dot. You have never seen this extra term here. But now, all of a sudden, I have this extra term. Okay, so when is it that this alpha is equal to omega dot, just like what we have seen in the past, and I do not have this extra term here that you can see? When is that? One, when, as it says, the secondary frame does not rotate. If the second frame does not rotate, then these vectors ijk have constant magnitude and constant direction. So they have no time derivative, therefore alpha is only due to change in magnitudes of omega x, y, z, so alpha is simply omega dot. Another case is if the secondary frame is body attached. It is attached to the body. So if this guy is attached to the body, then since it is moving with the body, the angular velocity of the second frame with respect to the primary, this cap omega, is equal to small omega. And so here you're going to have a small omega cross a small omega, which is what? 0. Okay? So in two cases, the simple formula that we had, alpha equal omega dot, is the case. One is if we are measuring the angular velocity of the rigid body with respect to a non-rotating frame, we are measuring the angular, we are measuring the angular velocity of the rigid body with respect to a frame that is not rotating, or we are measuring it with respect to a frame that is attached to the rigid body itself. Well, the second case is so obvious, of course. If I'm measuring it with respect to something that is attached to me, that sensor is rotating with me. It cannot see anything other than the change in magnitudes. It cannot see the change in directions. The other thing, the first one, is when omega is 0. Now pay attention. When omega is 0, it doesn't mean the secondary frame does not move. It can move. It cannot rotate. So it can translate. So if the secondary frame is just translating along XYZ without any rotation, still alpha for that, alpha written in that, is going to be omega dot. And the other thing is, if I somehow know the relative omega, if I know the omega of the rigid body in general case, if I know the omega of the rigid body with respect to the secondary frame, and I call it omega relative. So I know exactly how this rigid body is rotating with respect to the secondary frame, I call it omega relative. And I know how the secondary frame is rotating with respect to primary, I call it cap omega. Then omega of the rigid body with respect to the primary is going to be sum of those, right? Just like when we added velocities together, remember? Relative motion, V of A with respect to B is V of A with respect to C plus V of C with respect to B. So in this case, omega of the rigid body with respect to ground is omega of the rigid body with respect to the secondary frame, the sensor, whatever it is, plus the omega of that secondary frame or sensor with respect to the ground. It's a vector. We can easily use addition of vectors. Now, to see the application of this and this guy here, I would like with you to go through example 23, which is a very good example to discuss these two important kinematics formulas and the typical formulas that we had in the past, and then we go through kinetics. Okay, so remember that the two formulas that we had in the past, that if you have a rigid body, so let me make it 3D because we are talking about 3D. So if this is point A and this is point B, and this rigid body has angular velocity omega and angular acceleration alpha with respect to the rigid frame, and this vector connects point A to point B, which we called R of B with respect to A. All the formulas we derived that related velocity of B to velocity of A and acceleration of B to acceleration of A, they are still valid in 3D. Those formulas are not limited. Those are not limited. So I can still say V of B is V of A plus omega of the object cross R of B with respect to A. This formula is still valid. And if I say A of B is A of A plus alpha cross R of B with respect to A plus omega cross omega cross r of b with respect to a, this guy is still valid. So please pay attention here about this centripetal term. I'm not writing it anymore as negative magnitude omega squared r of b with respect to a. In 3D, that simplification is not valid. In 3D, you have to carry out this cross product twice. So please pay attention. In 3D, you are not going to write it as negative omega magnitude squared r of b with respect to a. This is not equal to this in 3D. Do not use that, okay? It's only valid, that formula, for 2D cases. Use the general formula case. So both of these formulas still valid in 3D. No difference. So kinematics of 3D and kinematics of 2D are not significantly different. Now let's look at that in this example. So here you have, that's an interesting example, a bent bar, and it is attached to this vertical shaft. So here is welded. So when this vertical shaft rotates with angular velocity omega naught about the y-axis, this bent bar does rotate with it. And then at the end of this bent bar, you have a circular disc that can spin about this axis, and it is in contact with the ground, so it can have a rolling motion without slipping. And what we want to find is, if I give you omega naught as a parameter that is given, and the length h, length b, radius r, and angle beta are fixed quantities that we know they are, you tell me, first of all, what is the angular velocity of the disk with respect to the ground, and then what is the angular acceleration of the disk with respect to the ground. Okay, so what is omega of the disk? What is alpha of the disk? Okay, and here the problem is giving you some coordinate frame to use. So the problem says, at this moment, consider your secondary frame origin to be at this fixed point B, with x-axis along this portion of the bent bar, z to be perpendicular to that, and y to be upward. So here you have this secondary frame xyz. Now what is the secondary frame? It is attached to the bent bar. So when this bent bar rotates about this vertical shaft with omega naught, this coordinate frame also does that rotation, okay? But what we want is omega and alpha of this disk with respect to a fixed frame that can be just like xyz, but despite xyz that are rotating about this y, that fixed frame does not rotate. Okay, so what I will do is I will copy this here into the Microsoft OneNote, and we'll try to find this problem, solve this problem together with you. So this is what the problem is asking, and again, as I said, the goal is to find omega and alpha of the disk with respect to a frame that is attached to the ground. So I can put the z-axis of that to be on the same direction as z-axis here. I can put the y-axis of that to be the same direction, and x-axis to be in the same direction. Okay, now it does not mean that these axes always stay on the top of each other. No. As time goes a little bit, the capital XYZ is not going to move, but the small xyz is going to rotate. So the direction of small y is going to be on the top of capital Y, but the small x and big X and small z and big Z would have different directions. Okay, so this is the frames that we are using. Again, the one in blue is primary frame, the one in black is the secondary frame. So my goal is to find omega of this disk with respect to this cap XYZ. Well, I say if I can find the omega of the disk relative to what? Relative to this frame XYZ. So if you want, I can use this notation. Omega of the disk in cap XYZ is equal to omega of the disk with respect to small xyz plus omega of this small xyz itself with respect to capital XYZ. Right? Relative motion. Now let's see if I know them. What is omega of the disk with respect to the small xyz? And what is omega of the moving frame with respect to the fixed frame? Well, the second one is easy. We know since this small xyz is attached to the band bar, it is rotating with omega naught, and it is in the direction of vector j here. So this is simply omega naught j. Now, when I say j, we have to clarify what j are you talking about? Is that the unit vector along the small y or capital Y? And does it make any difference? Well, in this case, no, because small y and capital Y are on the top of each other, so that j is not going to be any different. This vector is j. Okay, so no difference about j. But when I talk about I and k, I'm talking about the ones along the small x and the small z. So this is k, and this k rotates with omega naught, and this is I, and this I also rotates with omega naught. Because I want to describe the motion of this disk with respect to this rotating frame XYZ small. So I use the unit vectors of this small XYZ coordinate frame to describe this guy here. So what is that? Well, it is along this axis, right? So you know when this guy goes this way, correct? And this point moves to the right, that requires that this disk goes like that, correct? So this is the omega relative, right? That's the omega relative. It has to go this way so that this point A goes to the right, and that matches this motion omega naught. So this is V of A. Now, so it is along an axis that goes from this point to this point. If I can determine that axis in terms of ijk, then this magnitude omega naught times the unit vector of that axis will be omega relative. Now, what is that? Well, you know, this bent bar is on a plane formed by what and what? By x and y, correct? So it has this unit vector here, if I draw it for you. This unit vector can be projected on the x-axis and on the negative y-axis. And the angle of that is beta. So this component on the x-axis is cosine beta. This component on the y-axis is sine beta, although negative. And this omega relative, if you use the right-hand rule, you see that this omega relative is basically from A to this bend point, right? If you use your right hand. So you see that it is rotating about an axis that is actually in this direction, not in the green vector direction. It is backwards. It is along this axis. So if I want to write that vector, then it has still cosine beta along x, but it has positive sine beta because it is going upward. Or I can call it, well, it is negative x and positive y. So there are two ways I can write it, but again, it doesn't matter. So it's going to be negative omega relative times this unit vector in green, which was cosine beta I negative sine beta j, and then plus omega naught j. And if you simplify it, it is going to be negative omega relative cosine beta I, and then plus omega naught plus omega relative sine beta, the whole thing times j. Okay, so this is the omega of the disk as measured with respect to the cap x1z, xyz. Now the question is, how much is this omega relative? So we've written it in terms of this omega relative, but this omega relative itself is an unknown. I don't know how fast this disk is rotating with respect to the bend shaft. So we have to find it, and to find it, we're going to use kinematics. So this is what we do. I am going to consider a point, so this point is A, and I consider a contact point here B. Or this is B, let me call it C. And then I'll relate velocity of C to A, okay? As I said, the formulas of kinematics that we have seen in the past, they are still valid, so I'm going to use this guy here. And I say that, well, V of C is equal to V of A, because they both belong to the disk, plus omega of the object cross R of C with respect to A. Now the question is, which omega would you put here? Since this CA and this RCA, these are measured, especially V of C and V of A, these two guys, is velocities of these points are measured in the world coordinate, in the primary, in the cap xyz. This omega has to be measured in cap xyz as well. Okay, so this omega that you're using here, it is going to be the same omega that we just calculated. So this guy is that omega of the disk as measured in cap xyz. Because this VC and VA are absolute V's, so this omega has to be absolute, means with respect to the fixed frame. Now what is V of C in the fixed frame? Well, C is a contact point, and this is rolling without slipping, so V of C is 0. What is V of A? How can I find V of A, this point? Well, A is rotating about the J-axis, and as I said, the velocity of that is in this direction, and the magnitude of it is what? It is going to be omega naught times the distance between A to this y-axis. So if I can find this axis from here to here, whatever it is, d times omega naught is going to be velocity of A, and the direction of that clearly at the moment is going to be what? Opposite to the z-axis, right? Correct? Because this vector here, this vector is on the xy plane, and when you say omega cross r, it's going to be perpendicular to the r, and it is going to be what? Along the negative z-axis. So it is going to be negative z, or negative k, and then d times omega naught. But how much is d? If you look at this picture, d is h plus what? B times cosine beta. So this d is h plus b times cosine beta. If I multiply that by omega naught in the negative z direction, that's v of a. So v of a is negative h plus b cosine beta times omega naught in the k direction. And then omega cross r of c with respect to a. So omega is this vector here, right? Whatever it is, we write it down. Negative omega relative times cosine beta I, and then plus omega naught plus omega relative sine beta j. This guy here cross r of c with respect to a, which is the vector that connects a to c, and that is this vector here. If I can use a color to show it, that's this vector. This is r of c with respect to a, and if I write it here, the magnitude of it is r, and the direction of this vector, what's your guess? What would you say? What is the direction of c with respect to a? Is that along the j-axis? The answer is no. The direction of this vector is perpendicular to the direction of this bent member. So this r is basically having some component along x, and it has some component along y. So it's not pure y, it has some x and y. How do I find it? Well, you can either do it here, or if you look at this guy along the z-axis, if you look at this mechanism along the z-axis, this is how it looks like. Okay, and this angle is beta, and this is 90 degrees, and this is this vector. So in order to project this vector, you need this angle. Magnitude of it is r. What's that angle? Well, since this is vertical, perpendicular to horizontal, these two are perpendicular to each other, so this angle is also beta. And clearly you see it has an r cosine beta component in the negative j, and it has a negative r sine beta component in the I direction, right? So both components negative. So this vector, it is going to be negative r sine beta I, negative r cosine beta j. So now these are equal to each other. And guess what? Two vectors are equal, therefore the i's are equal and the j's are equal. Now, let's make sure everything looks fine. I guess it is. So now we can carry out. So here you have I plus j cross I plus j. So the I cross I and j cross j's would go away. And here you're going to have this I component cross this j component to give you a k. And then you have this j component cross this I component to give you a k, or negative k. And then with this k, everything is k. it's supposed to be equal to 0. Therefore, you can find the unknown omega relative. So if I do it, you will get the component of k here is 0. On this side it is, or if you want, you can take this negative term to the other side. It's up to you. I would take it to the other side because it does not depend on the unknown. So it is going to be h plus b cosine beta times omega naught. Now on this side, what do I have? I have I cross j, so it's going to be k, but this is a negative and this is a negative, so it's still k. So the magnitude is going to be r cosine beta times omega relative cosine beta. So this is going to be r cosine squared of beta times omega relative. And then I have j cross I, which is negative k. With this negative is positive k. So it's going to be r sine beta times this. Right? So it is going to be r sine beta omega naught. Right? R sine beta omega naught. And if you want, I can take it to this other side. So make it negative r sine beta omega naught. So let me take it to the other side. So add another term here, negative r sine beta. And then here I have omega relative r sine squared beta. And when I simplify this, it is simply going to be r, right? Because if you factor it, it's sine squared plus cosine squared. So r omega relative is going to be h plus b cosine beta minus r sine beta omega naught. So if you divide your omega relative, it is going to be h minus b cosine beta minus r sine beta. Actually, this is plus, divided by r, the whole thing, times omega naught. Okay, so this is the magnitude of that omega relative here. And if you want, you can simplify these two r terms, but that's exactly the answer you see in your textbook. And now that I have this omega relative, I can come here and put it back in here and in here in terms of magnitude and find the omega of the disk. So if I plug that omega relative I have here, this guy, if I call it equation star, if I put star in here, this is going to be equal to, and simplify, the omega of the disk with respect to the world frame, it is going to be, let's see if I have anything. I don't. So if I want to do it, it is going to be a big thing, but I can do it if you want. So omega relative cosine beta, it's going to be all in terms of omega naught. So h plus b cosine beta. Okay, maybe that's not the best idea to replace it, but that's fine. So it is going to be some big omega naught times. Now here, negative of h plus b cosine beta minus r sine beta divided by r, this whole thing times cosine beta I, and plus 1 plus that sine beta. is going to be 1 plus that whole thing sine beta times j. Okay, so this is going to be omega of the disk with respect to ground, right? So you see, although the problem looks very simple, the geometry is not super complicated and everything, and the rotation is a simple omega naught, then the omega of the disk with respect to ground is a little bit more complicated in terms of the geometry and everything. Okay, so that's omega of the disk with respect to the ground that we found. Now the problem is asking about alpha of the disk. It says what's alpha of the disk with respect to the frame XYZ? And this is d over dt of omega of the disk with respect to the frame XYZ. So we have to take derivative of what we found over there, and we can do it, right? So we can either come here and directly take derivative of this big thing here, which I found. Where is that? Here. Can directly take derivative of that, where omega naught, remember omega naught is constant. So this term has no derivative, but this term inside this braces has derivative. Which term has derivative? Well, if you look, h is constant, b is constant, r is constant, beta is constant. So this whole thing, if you want, if you would like to call this whole thing here, I can just call it whatever you want. A, this is just a constant A, and then this whole thing here, I can call it B. By the way, this J has to come out of the brackets. So I can simply call it omega naught AI plus BJ. That's this guy here. And again, A constant, omega naught constant, but remember I and J are not. So when I take derivative, it is going to be, since I and J are basically attached to the frame that is itself rotating with angular velocity cap omega, which in this case is omega naught J, so they have time derivative. So it is going to be a omega naught di over dt plus b omega naught dj over dt, where again di over dt is going to be omega naught j, because that's this vector cap omega cross I, and this is going to be omega naught j cross j, which is 0. And j cross I is k, so at the end of the day you will get negative a omega naught squared in the k direction. And you have to bring a and simplify, and that's going to be the answer that you would get, right? So you can write it as negative omega naught Okay, and again, remember A was this negative h over r, the whole thing times cosine beta. So h plus b over. And then there was a cosine beta term as well involved. We need to bring this a little bit to this side and multiply this whole thing by cosine beta. Okay, so this is your alpha, and that's it. Okay, so again, time consuming, takes time, but that's how you deal with kinematics of 3D objects.